Hello everyone and welcome to this fourth lecture on analog integrated circuits. Today we are going to talk about the loop gain pole products, and this is actually a two-day lecture. So the topic of today will be, or these 2 days will be the following. First, we're going to talk about how we implement the ideal amplifier that we introduced in the previous lectures, the Nuller. We're going to talk about different amplifier configuration stages. We start with the common drain. We will talk about the common gate amplifier, series and shunt stage amplifiers. We will have two examples of series and shunt stage amplifiers that we are going to analyze using the asymptotic model. And then we are going to talk about other single stage amplifiers that are also interesting for us. Now we have that the Nuller can be in principle implemented using a combination of different electrical components. Now we have to remember that passive devices like resistors, capacitors and inductors, they do not provide any power gain, and therefore we should avoid use them inside our Nuller unless it is strictly necessary, and when it's necessary, for instance when we are doing compensation. Then we have active devices. They convert DC power to AC gain, but we have the problem that first they are non-linear, and second they come also with capacitors and they add poles to the system. So somehow they also limit the bandwidth of the whole system. So we introduce a figure of merit that relates both the gain and the poles that active devices provide, because we can put these devices in different configurations, and these configurations will give us different gains and different poles. So by introducing this figure of merit, we can do fair comparisons of which devices we should use in order to implement our Nuller. So we introduce this gain pole product, which is a very interesting and very important figure of merit when we design analog circuits. So let's start with single stage amplifier configurations, and then we have already studied a little bit about the common source stage. The common source stage does not have feedback if we don't consider these CGD capacitance that appear between the gate and the drain. It is a stage that does not have feedback. So we will call it a non-feedback stage, and it is a very basic amplifying stage that we study. Then we have it here down. We have our common source stage. So why we will call it common source stage? It happens that the source, it is connected to a common point, and typically the common point in most analog circuits it is ground. So many nodes, many terminals in electrical components are typically connected to grounds in a circuit. So this is a common node for many devices. So when we connect the source of the transistor to ground, and we use this transistor as an amplifier, we will call it a common source stage. And then we have it here, the two-port model for this amplifier. If we consider that it is an ideal amplifier, the two-port model will be like this. We have that one terminal it is common at the input and at the output. That will be the ground terminal. Okay, so we already studied a little bit about this, the intrinsic gain characteristics, the ABCD parameters, and the position of the poles of this configuration. Now we are going to study the common gate and common drain configurations. And we see that we can describe these stages as some variation of the connection of the common source stage. So we can actually build the common drain stage by taking a common source stage and connecting it a little bit different. So for instance, a common drain stage, we have an analogy with the buffer, the voltage buffer. We can replace the nuller with the transistor, and then we will see that our common drain stage is being formed. Why it is called common drain? Because now I have the drain connected to my common terminal, that it is a common node for many parts of an analog circuit, that is going to be a ground terminal. We can do the same for the common gate. We have an ideal buffer built by a nuller, so we have a current source here. This current is going to flow in this direction and going out like this. And we replace the nuller by a transistor, a common source representation or transistor like this. Then we see that this is also going to behave as a current buffer. So this current is going to enter in the transistor and leaves like this. It's acting as a current buffer. So we have a voltage buffer here. This voltage here is the input, and the output voltage is going to be located here. And we're going to study the characteristics of these amplifiers. So precisely as we did with the common source stage, we will calculate the gain and the position of the poles. So we start with the common drain stage amplifier, and we are going to use the asymptotic model to study the characteristics of this amplifier. So we take again the asymptotic model. We have something like this. Actually, we have a series impedance here, and then we have connected the load here. Okay, and then if we consider that this amplifier is ideal, then we will be extracting the asymptotic gain, considering that this amplifier is ideal. So in ideal amplifier, we have that input voltage will be equal to the output voltage. In this particular case, there is no current flowing in this direction, so the voltage gain in this case, assuming that the gain is infinite, the asymptotic gain, it is going to be equal to 1. Okay, so we have part of our calculation totally done. Now let's move forward, and then let's see what happens if I replace the nuller with a transistor, and then we have the small signal model for our transistor here. And let's start analyzing this circuit. Now, for the asymptotic model without a nuller approximation, if we consider only that the amplification comes from the transistor itself, we will have that we let our transconductance, that is the amplification parameter, go to infinite. Okay, we let this one to go to infinite, and let's see what happens. So one of the things that will always happen, and I will draw the transistor here. Okay, so we have plus, minus, minus, plus. That will be VGS, that will be GM, VGS. Okay, so one thing that will always happen when we place a nuller in a negative feedback configuration is that this voltage is going to be equal to 0 volt. When we assume that we have an ideal transistor also with infinite transconductance connected in negative feedback, this voltage will also be equal to 0 volt. Okay, that is something that will always happen because of the presence of the negative feedback itself. So when we set the transconductance to infinite, this is starting to behave like an ideal amplification. We have that this voltage VGS is going to be equal to 0 volt. So we can put here, this voltage is equal to 0 volt. And something very interesting happens. So the voltage is equal to 0 volt, there is no current flowing in this capacitor. So basically this capacitor is removed from the asymptotic model, assuming this configuration. Okay, so we have that this capacitor has been removed, but not CGD. CGD is still there. In principle, CGD it is not part of the amplifying stage here. So we can even draw it CGD outside of this dotted line. So what happened here? Now let's assume for a second, for simplicity, that I will ground this node here, which is the typical case. We'll see that this node that it is grounded, it is also grounding this terminal of the capacitor CGS, and then we will have at this impedance here appears in series with CGD. It appears in series with CGD, and we can actually draw it like this, be in theta S, and then we have a capacitance with one terminal, CGD, with this terminal grounded. So we have the following circuit, and then what we have here it is that for the asymptotic model we will have that this system will introduce one pole, assuming that theta S is resistive, of course. If this is a resistor, we will be introducing a pole in our asymptotic gain. So think about this. Even if we consider this transistor ideal with infinite transconductance gain, there will always be something that is limiting the gain at higher frequencies because of the presence of the capacitor CGD. Regardless of how large is the transconductance, we are filtering the signal that enters in the amplifier at high frequencies. And this is the position of the pole. It will be like this for a resistive input series resistance. That will be plus S CGD times RS. Now remember what we talked before. A pole in the asymptotic gain becomes 0 in the loop gain, and actually become a phantom 0. So we will come back to this very soon. Now we have done the calculation of the asymptotic gain. Now let's take a look to the loop gain. to calculate the loop gain, I'm going to follow the next steps. So we have our small signal model here. What I'm going to do now, it is I'm going to replace this part here that we have here, that is the gain part here. We're going to replace this by a constant value. So what we're going to do is let's see like this. We're going to replace this one by a constant current source, okay, with the same direction, and I'm going to call it this one a test current source, IT. Okay, so we are replacing this variable here with a constant current source, and then my objective will be now to see how much of the current that I have applied here comes to the terminals VGS. And when I calculate this one, this is going to be my feedback, my beta, the beta factor. When I find that one, I can come back and calculate the loop gain that will be equal to my beta factor times my transconductance. Yeah, so this is a very interesting method because I am not breaking the loop in as we did in using other models, and it is a really powerful thing because all the load in it is embedded in our calculations now. So how do we do that? We replace this one. We replace the voltage control current source by a ideal current source, and the circuit that we have is the following. And we remove the input voltage source. So we set this one to 0. We set this one to 0. So we redraw the circuit. We redraw the circuit, and then this is the resulting circuit that we have when we redraw this circuit by replacing the voltage control current source and setting this one to 0. So this is the resulting circuit that we have. Now we calculate the VGS voltage, and normally the calculations are very simple. So there is nothing special technique that is required. So typically it's current dividers and simple voltage divider that need to be calculated. So here we're going to calculate the current that passes through this branch. So we have this current flowing from this node to this one. So we can calculate the current that passes through this branch. So that will be equal to IT times all the impedance in the other side. That will be RT S in parallel to zeta L. Okay, that will be the voltage. That will be the voltage in this node. And since we have here a capacitor, this is an open circuit, the current actually is going to be 0. So all the current it is actually diverted here, and this voltage will appear also here. Okay, so there is no current flowing through zeta S. That means that this voltage and this voltage have to be the same. Okay, so we have that the voltage that it is going to be created here goes in this direction, that it is opposite to the arrow and minus, the plus and minus that we have here. So this voltage will be minus, and then we have VGS. So very simple calculation. Okay, so now I found VGS. I divide VGS divided by IT. Okay, that will be equal to minus RDS in parallel with zeta L. So on this transfer function from IT to VGS, it is my beta. And this is beta at lower frequencies, so because I have not considered the capacitors. Okay, so as we see, it is quite simple to do this calculation. Now we found B0, beta, the feedback factor. We can come back and get the transconductance. So now I can multiply this one by the transconductance, and then I get the whole loop gain. So two steps. First, I remove the transconductance and VGS. I put a test current source here. I set the input to null, to 0, and then calculate what is the amount of VGS that comes back. And then I multiply back by the transconductance, that is my amplifying variable, and then I get the total loop gain. Okay, so now we have loop gain here. We have the asymptotic gain that we calculated before. We can do some interesting conclusions here. So the closed loop gain of an amplifier, as we defined, it is equal to minus the asymptotic gain times we have the loop gain here, that is positive here, minus AB here. Okay, this is what we have. So for the common drain amplifier, that will be 1, the one that we calculated, the ideal, and then we will have minus GM times RDS in parallel to, and then we have zeta L here, so we can put it assuming that my load is resistive. So if zeta L equal to RL, then we will have the following here. Okay, and then 1 minus GM times RDS in parallel to RL. Okay, so at the end of the day, what we have is that that will be equal to GM times RDS in parallel to RL, and then 1 plus GM times RDS in parallel to RL. Okay, and if RDS it is much higher than RL, we can simplify this. This might be typically the case. GM RL divided by 1 plus GM RL. Okay, so this is the voltage gain that we have for our common drain stage amplifier using the asymptotic model. So this is calculated using the asymptotic model. Asymptotic model. Okay, let's do it very quickly using a traditional classical circuit theory, so you get a grasp of that. Using the classical circuit theory. Let's see. Classical method. In the classical method we have the following way of doing the same. So we have GM VGS plus minus VGS, and here we will put the load, and let's omit for a second the RDS for simplicity. Let's assume that it is very large. Have it out, and then we have here V in. So then we will have that V in is equal to VGS, that is the voltage drop here, plus the voltage drop here. That will be GM times VGS times RL, and this is equal to VGS 1 plus GM times RL. And then the output voltage will be, in this case, only GM times VGS times RL. So when we calculate the voltage gain, that will be V out divided by V in, and that will be equal to GM VGS RL divided by VGS times 1 plus GM times RL. This goes, and then we have exactly the same. So both methods give us exactly the same result times RL. This is exactly the same that we found by using the asymptotic method, but the asymptotic method has many advantages. For one thing is that it gives us information about the loop gain that we have. It gives us information about the asymptotic gain, and it gives us information about the zero that exists in the loop gain. And when the circuit became more complicated, this is going to be much more easier to calculate than doing classical circuit analysis. So we will have some examples on that. Okay, some conclusions until now. The positions of the poles and zeros can be found rather quickly. For the position of the poles, we will use open time constant, and we will have an example very soon to see how we can do that. If the source impedance is resistive, then we will have a zero located in minus RS CGD. Okay. This is actually something that we predicted already when we calculated the asymptotic gain, so we immediately see that there is going to be a pole there. So this will be a phantom zero. Every time that we see a pole in the asymptotic gain, it becomes automatically a zero in the loop gain. Now, the only parameter that it is set by the feedback, it is parameter A, that it takes a value close to 1. So we can see here that this AB is always going to be smaller than 1, and for very large loop gains it is going to approach to 1. So it's a value close, the A parameter takes a value close to 1. The other parameters are almost the same as in a common source state. They have not been touched. Another conclusion, it is that the DC feedback is ineffective if the source impedance is very large. Why? Let's take a look to the circuit again here. we take this one here. We have said that this voltage here appears here. However, if this impedance is extremely large, in particular if it is not resistive, then the feedback gets broken. Then what we will have is some capacitive divider here. So this calculation does not apply anymore. Then the gate will be disconnected from the drain, and then there's not going to be effective feedback there. We can see it from another point of view also. If the source impedance is extremely large, this is a very bad model for the source. It will not be a voltage source, the one that we should have put here. If the impedance is extremely large, the correct model for amplification should be a current source. So we will not need a voltage buffer, but other kind of amplifier handling this. So very large impedances here make the voltage buffer ineffective. So it will not work very well for very large impedances. Very important to remember. The selection of the source and the load impedances, it is very important. It pops us here that bad selection of the source that makes this stage ineffective. Another important thing is that the DC feedback is ineffective if the load is equal to 0, and that is can be seen directly here. That if the resistance is 0, basically the feedback disappears, and also the gain. No, basically it is shorting the source to the output to the ground. Okay, so these are the conclusions for this stage. We move to study the common gate amplifier.